Would you all take your seat, please? Please take your seats. Mike Lecar joined SAO in 1965 at the invitation of Fred Whipple, and prior to that, he had served in the Navy, during which time he'd worked on Project Vanguard and used the Vanguard 1 satellite to make one of the earliest measurements of the J2 of the Earth, and cementing an early interest in planets and dynamics. He completed his PhD at Yale in studying stellar atmospheres, and after that was a founding member of the Goddard Institute for Space Studies. After Mike arrived at SAO, he remained here until his retirement in 2009. He was a member of both the Planetary Sciences Division and the Theoretical Astrophysics Division. And his work ranged from studies of tidal evolution to dynamical chaos of planets and asteroids, work he did with Fred Franklin, onto the formation of extrasolar planets. Mike played a key role in establishing the first astronomical observatory in Israel, something for which he was very proud. He was also a founding member of the Harvard Origins of Life initiative with Dimitar Sasolov. Mike taught generations of students in his freshman seminars. He attracted many, many people to astronomy, some of which have gone on to be chairs of astronomy departments. He served as a valued mentor and sounding board to many of us at the CFA and was kind of an elder statesman here. Mike, in his will, established for a series of lectures to be given in his name here at the CFA to encourage and recognize exceptional contributions to the study of extrasolar planets in particular and theoretical astrophysics in general. The previous winners have included Doug Lynn and Zvi Maze, who is here in the room, and we're honored to have him. This year's winner is Professor Eric Agol of the University of Washington, and he fits that description perfectly of making exceptional contributions to the study of exoplanets and theoretical astrophysics. I think if you don't know Eric's work, you will be impressed. Let me just say a few more things about Eric. He got his PhD in physics from University of California, Santa Barbara in 1997, was a postdoc at Johns Hopkins and a Chandra Fellow at Caltech before moving to University of Washington in 2003. As I said, he's made astonishing contributions to exoplanets, as well as, in particular, in theoretical astrophysics in general. You'll see all of this. I mean, you'll see, I hope Eric will highlight some of the amazing things he's done. But I really want to say something else about Eric, and that's that he consistently works in a way that facilitates other people's science. And I think that's exemplified by something that Casey Mandel and Eric did, many, many years ago, establishing a nice set of algorithms for determining light curves of transiting extrasolar planets. So if you've used the Mandel and Agol code, raise your hand. All right, everybody say thank you, Eric. Thank you, Casey. Because this is an example of something that we have all used numerous times, and it's really made our work much, much easier. And it's just one example of the many kind of generative acts that I think distinguish Eric from other outstanding scientists. And it's the kind of thing that I'm happy that we're recognizing with this year's Lecar Prize. So Eric's papers are not only clear. I mean, they're fantastic. They're full of guideposts, trail markers to leading everyone onto great things. So I have with that, let me just turn it over to Eric.
Can I hand you this? So I just need space. Okay, my speaker's on now. Well, thanks, Matt, for that introduction. It's really a privilege to be given this award. And if there's anyone that nominated me in this room, I'd like to thank you. I'd like to thank Mike Lecar, whom I never had the pleasure of meeting, and his family. And I'd like to start off with an interesting short story. So despite not knowing Mike, I think I've seen him around at the CFA. And when I heard about this prize, I thought, Lecar, that's an somewhat unusual name, but maybe common enough that it may be a coincidence that I went to high school with another Lecar. Matt Lecar. And then when news of this award came out, I think on Facebook, someone posted, "Isn't Mike Lecar Matt Lecar's uncle?" Turns out he is. So I went to high school with Matt Lecar, Mike Lecar's nephew, and Matt was brilliant. He's very talented in acting, singing, in academics, and a really interesting guy. 1 year ahead of me at the college preparatory school in California. So that was a nice coincidence. So even though I haven't met Mike, apparently his brother and him had a lot of similarities, and I think some of those were passed down to Matt. So, okay, so today I'd like to turn to the topic of transit timing variations, which is something I've been working on for, over a decade now. It sort of led out of the paper I wrote with Casey about transit light curves, and then thinking beyond that to what else you could learn from transiting exoplanets. So the plot I'd like to start off with is this from a review paper by Natalie Batalla in 2014, and it shows the scatter plot of planets detected to that date, which is, there'd be more points on here now. And this is plotted in mass and Earth masses versus orbital period. Oh, I'm not supposed to move, sorry. There is a pointer though. Okay, so mass of the planet and Earth masses, so Earth's down here, and orbital period in days from 1 to 100,000 days. And so most of these measurements have been made with radial velocity, which is depicted in pink, some with microlensing in red. There's some directly imaged planets out here in blue. Of course, the masses are just inferred from models, some green points from eclipse timing of binaries. And then these are blue and light blue ground-based transiting exoplanets, which have been followed up with radial velocity. And so that was the picture. This is basically this picture before Kepler. Now with the Kepler spacecraft, we can get planet radii from the depth of transit. So this is planet radius versus orbital period. And now we've just had this glut of abundance of exoplanets, and many of these are in multi-systems, so multiple transiting planets orbiting the same star. And this was, I think, many of us would say totally unexpected. There were some inklings from the radial velocity surveys that this planet population would be present, but the fact that these are all at much shorter orbital periods than Venus and Earth is a big surprise. And so we're still reeling from all this data and trying to make heads or tails of it. But one big problem with this is that a lot of these points we would like to put over on this graph of mass versus period. But we can't yet because we only have radius measurements from transits. And so a lot of what I'm going to discuss today is, can we get the masses for some subset of these planets? And we're just scratching the surface of that with transit timing variations. So this talk in many ways is a progress report. I'll review some of the history of the work on this, both theory and observational, and then spend a little time at the end pointing ahead to the future. So first off, would like to start with kind of an overview of the information that we get from a transit. And let's see if this is going to work. Okay, so as a planet passes in front of a star, you get a shadow cast in front of that star, and as the planet orbits across the star, then you get a little bit of blocking of that light, and so that reveals itself in the light curve of the star, which looks like a trapezoidal dip. And I didn't quite draw that correctly, but it straightened the lines for me, which is nice. Okay, so then this duration of this transit tells you about how fast the planet is moving across the surface of the star. And I should say that this is flux, and this is time axis. And I need to get rid of this straightening thing. And so, and the dips are typically 1% or less. Okay, so you learn that the duration tells you about the velocity across the surface of the star. That's related to the impact parameter, and the impact parameter affects the shape of this transit, which is the ratio of the duration of the ingress and the egress to the total duration of the transit. It's also affected by the orbital period and orbital velocity, if you know the mass of the star, and also affected by the eccentricity of the planet's orbit. Then, of course, the depth of the transit, as I mentioned, gives you the ratio between the area of the planet that's blocking, it should be a squared, divided by the radius of the star squared. Of course, the pi's cancel conveniently. You can add in limb darkening to this, which is what Casey and I did, and many others have done now. And that affects primarily the trough of the transit, which gives it some curvature. But the main thing I'm going to be talking about today is the timing of the transit, so kind of the midpoint of the nth transit of a planet as it goes around the star. The mean separation between those times gives you the orbital period, and of course from Kepler's law then you can get the semi major axis if you know the property of the star. But what we're interested in are deviations from that strict orbital period, okay, which occurs for a Keplerian orbit, but not if there's dynamically interacting planets. How do you measure that transit time? Well, you can't directly, but you can measure the times of ingress and egress and then take the average. So let me, okay, so, sorry, I'm doing a little editing up here on the fly. Okay, so let's say you have this transit light curve and you fit a model to it, which is shown in red there. Then if your model is off in the time of transit a little bit, then the ingress and egress are going to deviate. And so it's that difference in flux for the ingress and the egress, which is going to alert you that your model's poor fit. And so then you can optimize the model and shift it in time until you get a good match. And then at that point, that's the transit time. So the signal to noise of the measurement of the transit timing variations is related to what signal to noise you can obtain for the flux during the ingress and egress of the planet. There's a little bit of information if this transit is curved, but if you shift the transit in time and let's say you ignore limb darkening, there's not much change in that trough of the flux or the flux outside of transit. Now, of course, stellar variability affects all this, and that complicates the analyses, but basically it's the drop in flux and the rise in flux which gives you the transit times. And then if you measure these for n transits, then you can find, look for the ephemeris and look for deviations from this ephemeris. So the idea of looking for deviations from this ephemeris was pioneered in the early 2000s. Really, the first couple of inklings of it were by Jean Schneider. He had a couple of conference proceedings pointing out this idea. He didn't work through all the dynamics too carefully, but he basically thought of the idea. And I think the conference proceedings appeared in something like 2003, actually while I was working on this project. Jordi Moralda-Escudé had a nice paper on long-term secular dynamics and how that would affect transit timing variations on long time scales. In 2005, there were two groups that were in a horse race to look at shorter time scale transit timing variations. And we, of course, became aware of each other's work and decided to submit to the archive on the same day. And we submitted to journals about the same time, and they both appeared in 2005. One by Matt Holman and Norm Murray, and then the other by myself and Will Clarkson, who's now, I believe, a professor at University of Michigan in Dearborn, Jason Steffen, my first graduate student at University of Washington, who's now a professor at UNLV, and Rem Sari, who just left for Israel. I heard he's been spending a sabbatical, or part of a sabbatical here. And so these papers really made the point that transit timing is a very sensitive technique because it can measure very small changes in the phase of the orbit of a planet, and so it can be sensitive to very small perturbations. In particular, mean motion resonances can lead to significant perturbations that could be measurable potentially from the ground and then eventually from space with Kepler. And so these couple of papers sort of laid out some of the initial theory for this, which I'll now describe in a little more detail, plus the progress that's been made since then. Okay, so the idea of transit timing variations is fairly simple. You have a time axis, let's say in days, and then the number of transits on this axis. And so you measure the times of transit of the planet, and it should be mostly linear. I'm exaggerating the variations here. I'm putting a sinusoid on top of that. and then you fit a linear trend to this, subtract that off, and that gives you the remainder, which is what we refer to as transit timing variations. So that, let's see. Okay, so that's going to look like, when you subtract that off, it's going to look like a somewhat sinusoidal residual. Now, I came from the black hole astrophysics community, and so I wasn't aware that the eclipsing binary community already had their own terminology. So this is sometimes referred to as observed minus calculated. In this case, the calculated being the linear fit, and the observed being the actual transit times. Okay, so now if there's a planetary companion to this, let's say at roughly half the orbital period, then it will show its own ephemeris, and then I'm not drawing the spacing on these correct. It should have it more transits. You can fit that, and then you get TTVs, and then I've drawn these here to be anti-correlated, and that's just due to conservation of energy. If the orbital period of one planet changes outwards, then the other one has to change inwards to conserve total orbital energy. Okay, so now what these timing variations are telling us is that essentially we're getting a snapshot of the planet each time it passes in front of the star. And so the timing variation is the cumulative, due to the cumulative variation of the orbital elements, or the orbit of that planet as it orbits that star in the meantime during that entire orbit. And so this is a stroboscopic effect. We're only getting the timing measurements at every roughly orbital period of the planet. And so in general, what that tells us, let's say we have an edge-on planetary system, because if it's transiting, that's a good approximation. If you have multiple planets, I'll assume for now that they're plane parallel, which tends to be a good approximation for TTVs. Then the change in timing for the ith planet is given by minus the change in its true longitude, theta, divided by its velocity, orbital or rotational velocity. Okay, so what this means is that if you take a Keplerian orbit and you fit it to the entire orbit of this planet over this entire time scale, and subtract off that mean Keplerian orbit, then you're left with some delta theta. And if the planet is ahead of itself, so it's further along in the orbit than it would be relative to that mean Keplerian, then it will arrive a bit earlier. So that's what the minus sign is caused by. So this, again, I'm not supposed to move over here. Sorry, I forgot. So it's early when it's ahead of itself in its orbit, and then it's late when it's behind in the orbit. And then the magnitude of the timing variations just depends on how fast the planet's moving in front of the star as it goes in front. And to first order, then this is roughly a constant, just given by the mean Keplerian orbit of that planet. Okay, so that's the basic idea of transit timing variations. So how are these produced? So let's see. This diagram is going to try and illustrate one of the effects that occurs. Okay, so say we have, actually I have a different version of this. No, that's right. Okay, so say we have two planets orbiting somewhat close to one another, and the inner planet, of course, is orbiting faster, so it passes the outer planet. Then conjunction is when they both have the same longitude relative to the star, and at the point of closest approach, gravity is 1 over r squared, so this is when they're going to interact most strongly. Now, before the conjunction, this planet is being pulled forward in its orbit by the outer planet. It's also being pulled outward in its orbit. Let's just consider the theta component of this force. If you integrate the force equations twice, then you get that it's going to, so this is actually, this I'll call planet 1 and this one planet 2. So during the conjunction, let's say it's moving with a delta theta that's initially sloping down. During the conjunction, it's going to start accelerating forward, so you can see that acceleration here. And then as it passes through the conjunction, it will start to slow down, so you see that curvature here. And then it will asymptote to the mean delta theta. And so 0 is the time of conjunction. And what I'm plotting here is the difference between the mean longitudes of the planets, which if they're on circular orbits or nearly circular orbits, that's just their orbital longitude. And so you'll notice that this is an odd function. And you can Fourier transform that in terms of this difference in longitudes, and you get a bunch of harmonics of that. And so it turns out each of those harmonics will have different amplitudes that contribute to this function, and you can use those to then diagnose the mass of the perturbing planet. And I'll show this in equation form in a few slides. Now, for theta 2, exactly the opposite effect occurs. It's being pulled backwards before conjunction and forwards after, so you also get an odd function, but it has the opposite sign. And again, this can be interpreted as conservation of both angular momentum and energy. There's also the radial component, and you can show with conservation of angular momentum that even though this radial component actually peaks at the closest approach, so it's going to have an even function. When you conserve angular momentum, then the delta theta component, which is the only one are concerned about for transit timing, that will also have the odd shape, and it will have the same sign. So this in total is going to be due to both the radial and the azimuthal components of the force. The other thing is that after each of these conjunctions is complete, of course, the planets have slightly changed their orbital elements, and that's what this partially what this delta theta is. And so that means that the forces are slightly asymmetric across these conjunctions, and so that's going to lead to longer-term variations. And so this is just in the limit that the planets are on nearly circular orbits. Okay, so now if you give the planets some eccentricity, then you can treat eccentricity to first order as being a circle, which is the guiding center, which is really what lambda 1 and lambda 2 are, is just the mean orbital motion of the planets. And around that, there will be an epicycle that the planet executes to first order in eccentricity. It has the opposite sense, so it's moving. Did I draw this wrong? I did, sorry, I drew the arrows wrong. Let's say it's moving this way in its orbit, so then the arrows are right way. So it's moving faster at pericenter and slower at apocenter. Okay, so then let's say the orbits have some orientation such that, let's say pericenters, well, this is really in the co-rotating, or the mean motion frame of this planet, but I've drawn the epicycles at two different angles to indicate that these have different longitudes of periastron. Okay, so now what will occur, so there's really two relevant frequencies that are important. One is this synodic period, which is, because it's the difference between longitudes, you can write that synodic period as being the difference between, 1 over the difference between the frequencies of the two planets' orbits. And integer multiples of this are also important. The second term that becomes important when you introduce eccentricity is a time scale that depends on how close the orbital periods are to the ratio between two integers that differ by different integer. The most important one for first order in eccentricity is that they differ by 1. So if the period 1 divided by period 2 is the ratio of j to j plus 1, approximately, but not exactly, so it's near but not in a resonance, then what happens is that every time these planets pass one another, they'll be at one point in their epicycle. So let's say this planet's here, and let's say this one's here. Then, because they're not exactly at j to j plus 1, then the next time they have a conjunction, they'll be at a slightly different point in their epicycle. And so then the forcing on the orbit will be slightly different because they'll have a different separation than they did at the previous point. They're also at a different phase of their epicycle, and so that slightly changes how they respond to that force. And then as the conjunctions proceed, each of these dots is supposed to represent a conjunction, then you'll proceed about this epicycle and come back to nearly the same point. And then the whole thing will repeat itself. And so there's a period of, the typical period of transit timing variations is due to this effect. And that scales as 1 over, you can take the absolute value to make it a positive quantity, j divided by p1 minus j plus 1 divided by p2. And so when you're close to commensurability, this becomes a really small quantity, and so this period of transit timing variations becomes a really large, long time scale quantity, and that's that sinusoidal variation that I drew in the TTV plots. And it also tends to be anti-correlated between pairs of planets. Okay, so, all right, so that's just a little bit of theory. I'm going to go into a little more detail in a second, but so why do we care about making these measurements? Well, I mentioned we'd like to get masses. There's also quite a few other ideas that have been proposed. And you notice I'm using a mix of keynote and handwriting, and it's because my computer crashed a few days ago. So I had to write this on my iPad. Okay, so one cool thing is that because of this anti-correlation of these sinusoids, if you see two nearby planets that appear to transit the same star in the Kepler field, and they show anti-correlated transit time variations, then you know they're probably interacting and they're probably orbiting the same star and they're probably planets. And so this is a method of confirmation of multi-transiting planet systems, and it's been very effective in saying that these planets are actually planets and not just planet candidates, which Kepler was careful to distinguish between. And so there's been several papers, this is just a subset, written by the Kepler TTVs and multi-planet team, confirming planets with transit timing variations. One of the first applications that was pointed out was you could use this as a way to detect non-transiting exoplanets. And so I'll talk a little bit about some of those recent detections, or first detections actually, one of which was here. And then, of course, the main topic I'm going to be discussing today is constraints upon the masses of the planets, but you also can get constraints on the eccentricities of the planets from the pattern of that end phase of that sinusoidal TTV. There have been some papers pointing out that you could use transit timing variations and also duration variations potentially to detect exomoons orbiting transiting planets. And then we mentioned this, and then a couple other papers, one by Ben Monte and John Johnson, about combining transit timing variations and radial velocity measurements to measure the absolute masses. So effectively it becomes like an SB2, a spectroscopic eclipsing binary with both components detected. Now, there are drawbacks to implementing transit timing variations, which are significant. One is that you need long time monitoring, and it really wasn't until Kepler that we got that provided to us. You need good timing precision. Kepler also gives good timing precision for some planets, and those I'll show some examples of. Another drawback is that there are degeneracies. There's a period degeneracy if only one planet transits. If you're trying to detect a non-transiting companion, you can put it near different mean motion resonances and get the same sinusoidal signal. There's also an eccentricity degeneracy, so you can change the amplitude and phase of the epicycles of two planets and get the same sinusoid out. So that's another potential degeneracy. There is a way to break this, though, or there may be ways to break this. I'll show you one way to break this. There's also a mass eccentricity degeneracy that occurs due to aliasing of the two signals that I showed you. A fourth drawback is that transit time variations, if they're large enough in amplitude, will spread out the times of transit. And so when you fold a low signal to noise transit to try and build up the signal to noise with time, transit time variation smears out that signal and it reduces the signal to noise. This was pointed out by Garcia, Melendo, and Lopez Morales a few years ago. Okay, so these are some of the potential applications and some of the drawbacks, and I'll give some examples of these applications, and I'll give some examples of ways we're combating these drawbacks, all time allowing. Okay, so this mass eccentricity degeneracy is a barrier for measuring masses. And this was pointed out in a very elegant paper in 2012 by Yoram Lithwick, Yangxin Wu, and Jiwei Shi, I think I pronounced it right. Let's see, so they pointed out effectively what is that, so they discussed this TTV period, and you can treat that, you can rewrite that as a frequency at 2 pi over the period, and that's equal to j times n1, where n1 is equal to 2 pi over the period of the first planet, so that's just the orbital frequency of that planet, n2 for the other planet. So let's see, it's the difference between these two frequencies multiplied by j and j plus 1 that gives you the low frequency TTV because it's a long period. So unfortunately, when you observe a transient planet, like I said, you're observing it every single orbit, and so the position in that orbit for, let's say, the inner planet is always going to be roughly the same longitude because that's when it passes in front of the star. And so it turns out you're insensitive to the frequency of the transiting planet, which means that the outer planet you can detect. The aliasing causes frequencies to be mixed that appear exactly the same to the observer, and yet they're different in real frequency space. So, for example, if you had the harmonic of the synodic period, j plus 1 times n1 minus n2, for the inner planet, that will look exactly the same as this resonant term. And so the aliasing of the synodic and the resonant terms turns out to cause a degeneracy between mass and eccentricity measurements. And so in this paper, they showed that there are basically, for two-planet system with both showing sinusoidal TTVs, there's basically four quantities you can measure. There's two mass ratios, and then there's an eccentricity vector that they expressed as a linear combination of the eccentricity vectors of the two planets, so that linear combination is two components. Okay, so four quantities we'd like to measure. But then they showed that the amplitude of the sinusoidal variations, I'll just write delta t for the inner and outer planet, it scales as the mass of the companion planet to the mass of the star times the j of the nearby resonance, and the plus or minus means that they have opposite signs, times a factor that depends on the period of TTVs divided by the period of whichever planet is transiting. So this is well determined, but then you have to add to that a factor that depends on the eccentricity vector, and they used a complex notation, so that's why I have this star, times the period of the TTVs divided by the period of the transient planet squared. And that's important because if this is very long, if you're really close to a resonance, then you can get a really long period of TTVs, then this can be a really large factor. And so even if the eccentricities of the planets are small, this factor can be comparable to this factor. Now, the good thing is that this has complex and this is real, so any change in the phase of those sinusoids will reveal that it's due to eccentricity, and this phase turns out to be fixed. Now, the reason this is important is because we'd like to measure this mass term out front, and so because if there's some degeneracy in the real component of this eccentricity term, then that means we can trade off eccentricity and mass ultimately. Okay, so another way to say this is that there's four unknowns, but we have three observables. We have the amplitudes of the two planets, and then we have one phase if they're anti-correlated. So this leads to a mass eccentricity degeneracy. If you have very precise data, and you can actually, these will give slightly different phases, and then you can break that degeneracy. But that sort of signal to noise isn't always present. So this is really kind of a signal to noise problem. The aliasing I just wanted to review. So this the synodic frequency, here I have the second harmonic of that is plotted in black here, so that's a high frequency term for the inner planet. And then this is TTVs in arbitrary amplitude. And then I've taken the resonant term for 2 to 1 and plotted that here. And so notice that for the inner planet, there's the same dependence on N2. Both have a minus 2 N2. And so because we're sampling at the frequency of the inner planet, then these two terms are going to be aliased. For the outer planet, if I take the synodic frequency variation, sine N1 minus N2 times T, that's this black curve here, and then take the same resonant term and plot it here. Then for the outer planet, these both have the same dependence on the frequency of the inner planet. And this outer planet, even though these terms differ very significantly in frequency, we're sampling at that rate, and so those two will be aliased. And so when you sample at the transit times, then what you see are two identical sinusoids if these had identical amplitudes and phases. So the red is just sampling the red curve, and the black diamonds are sampling the black diamonds. Okay, so that's the problem that we're facing. Okay, so this assumed, though, that we just had that single sinusoidal variation. It turns out if you get good enough signal noise, you can detect other harmonics, always harmonics of the perturbing planet, and those extra harmonics can allow you to break this degeneracy. And so Kat Deck and I figured this out a couple years ago, I guess, because we started it here at the CFA when I was visiting in 2014. She was a grad student at MIT with Josh Wynn and worked closely with Matt Holman for her dissertation, and then spent a brief postdoc here 2 summers ago before moving to Caltech. So okay, so I've already mentioned that the non-resonant terms, like the sonic frequency, depend just on the frequency of the companion. That's actually true of the resonant terms, too. I should have deleted this non-resonant. And you can write this in the zero eccentricity limit that the transit timing variations scale with the orbital period of a planet, so this is for the inner planet, times the mass ratio of the perturber. You're always measuring the mass of the perturber. Times some functions of the semi-major axis ratio, which if we know the orbital periods, then we can get a good estimate of that. And then there's this sign of psi sub j, which is just the j, which is summed from 1 to infinity, times the difference in longitude. So this is the synodic frequency harmonics. And there's a similar formula for the outer planet, and these coefficients have opposite sign. Okay, so it turns out that if you can measure, so it turns out that the alias component is, in this example, the resonant term is aliased with this second harmonic of the synodic period for the inner planet and the opposite for the outer planet. But if you can get some of these other harmonics, then you'll see extra variations, and if you can measure those amplitudes, that can allow you to break this mass eccentricity degeneracy. And I'll show an example of that in a few slides. Okay, so, well, actually, I'll do it now. I'm going to skip a slide. Okay, so this came as a great discovery when the first Kepler, the first transit timing variation measurement that was really reliable. There have been a few kind of questionable claims in the literature with ground-based measurements of hot Jupiters. And this system was really spectacular. The Kepler 9 system, I think it's 2010, and 2 CFA folks, former CFA postdoctoral fellow Dan Frubicki, were prominent in this work amongst many other Kepler team members, and some of whom are present in the audience as well. So the neat thing about this system, it's 2, I'd say hot Saturns, I guess, is that the term, or warm Saturns at something like 20 and 40-day orbital periods. This shows a slightly longer data set, and the error bars are impossible to see. I think they're smaller than the data points here, which is kind of amazing. So the black points show the Kepler transit times with the linear ephemeris subtracted, so TTVs. And let's see, the black points have units of hours. And then I've done a harmonic decomposition of these and plotted one harmonic component, which is at that synodic frequency. Okay, and then this shows the outer planet, and you can see they're nicely anti-correlated. These are close to a 2-to-1 resonance, and the proximity to resonance actually determines this orbital period, or the TTV period, nicely. Okay. Now, this system is high enough signal to noise, again, you can barely see the error bars, that you can actually determine the masses of the planets fairly reliably just from this resonant term. There's a slight offset in phase, and that allows you to break that mass eccentricity degeneracy. That's generally not the case, though. These data are really exquisite. From that resonant fit, you can determine the mass of this outer planet from the TTVs of the inner planet, and then you can predict what that chopping signal at the synodic frequency should be, And so the red are the residuals of a harmonic fit to this transit timing variations. And again, I've just plotted that the component that's at the frequency of this outer planet. And again, it's aliased with this inner frequency, so that's the synodic component. So the red are actually the residuals of this fit. The blue is the predicted chopping signal given the mass that you measure from this resonant term, and it matches exactly. And so the cool thing about this system is it really gives us confidence that this is the right mass. That I may come to later about why we might not be confident in that. But this is a really great example in demonstrating this technique that you can measure the mass, at least of this outer planet, in two different ways, and you get the same answer from different harmonic structure in the light curve, or in the transit timing curve. All right, so that is an application of both that resonant and the chopping signal. Now, one of the next TTV papers was also led at the CFA. There's a theme in this talk. Much of this work occurred at the CFA. And that was led by a former graduate student, Sarah Ballard, who then became a Sagan Fellow at University of Washington, is now at MIT. And I believe second author on this paper is probably in the audience, is Dave Charbonneau here, her advisor. And so their goal was originally to characterize this transiting planet, Kepler, became known as Kepler-19, with Spitzer. So they did follow-up observations with Spitzer to make sure that there wasn't a blend that was diluting or changing the depth in the Kepler band. And so by looking at a different wavelength, you can determine that there's not a star of a different color that's modifying the transit depth. And in doing so, they found this surprise that the planet's orbital period was not exactly periodic. It showed variations from, these are transit timing variations in minutes, with an amplitude of something like 7 minutes or so. These were long cadence, 30-minute observations, and then they switched to short cadence, 1-minute observations, which gives you better timing precision. You better resolve the ingress and the egress in that case. Now, in fitting these data, they really could only, you can see the error bars are much larger, much larger than in the Kepler-9 case, and so they could really only fit one sinusoidal frequency. And so this was subject to the would be subject to mass eccentricity degeneracy. It's subject to an even worse degeneracy, which is that the second perturbing planet doesn't transit the star, so we don't know the orbital period of that planet. And so I believe Dan Ferbicki did these fits, but he found that there were a range of different orbits. So B is shown in black here, and a range of different perturbers matched these TTVs nicely. Unfortunately, in this case, the error bars are too large to detect that chopping signal, so we're not able to break the any degeneracies for this system. There are other systems, though, where you can do that. Okay, so this essentially was the first detection of a planet with transit timing variations, although a non-unique solution for the perturber. Now, this paper also had CFA involvement, led by David Nesvorny. David Kipping, I think, was the second author. This was a first case of a detection of transit timing variations, a perturber with transit timing variations with a unique solution for the perturber. So this planet has a period of somewhere around 30 days or so. And again, these are transit timing variations. In this case, though, like Kepler-9, they're huge variations. So this is in hours. So the amplitude, semi-amplitude is about 1 hour. The timing error bars you can actually see in this plot. And what you see here, the black points connected by the dots, doesn't look like a sinusoid. There's a lot of structure in here. You actually need 5 harmonics to fit this, with 5 harmonics again of the perturbing planet's frequency. Again, I've picked out the first harmonic shown in these red points here, and you can see that that looks nicely sinusoidal. So through an M-body analysis David Nesvorny carried out, and an exhaustive search of parameter space over all the different nearby resonances, the combination of all this harmonic structure gave a unique solution for the perturbing planet at a period of 53 days, again, non-transiting, and a mass of about 40% of the mass of Jupiter. with this mass and with this orbital period, you can then predict the synodic amplitude, and that's shown in blue, and you can see that goes right through this first harmonic. So again, it shows that this synodic chopping frequency is a nice diagnostic that you have the right answer. But it comes out of doing the full dynamical fits, of course. Okay. How am I doing in time? We started at... okay. Okay, so I started to get involved in this with a visit to the CFA in, I think it was 2011. And the godfather of this was Dave Latham, who decided to place me in an office across from Josh Carter, who was, I believe, a Hubble fellow here at the time. And we started talking about this problem of what if Kepler's missing some planets because of variations in the times of transit. And so through a Google search, I stumbled on an algorithm that actually allows you to find quasi-periodic pulses within a data set. And Josh has spoken on this before, so I'm just going to summarize. But this shows 65 transits of a planet that we identified in the Kepler data that the Kepler pipeline missed. You can see each transit is very low signal to noise. This is, the color represents the brightness of the star. Gray is missing data. And the transit times were varying by 5 hours. This is in hours here, with the mean orbital period subtracted. It has a planetary companion that was detected by the Kepler pipeline, and they show anti-correlated transits. And they show a lot of structure. In fact, you can see sudden jumps after the conjunctions, which is really constraining on the properties of the planets. The red is the best fit model. These data were so precise, in fact, that we got a very nice mass-radius relation for these two planets, which are close to a 6 to 7 period ratio. This inner planet's at 13.7 days. The outer one was at 16.3 days or so. And so from a full photodynamical analysis of this system, we get the masses and radii 1 and 2 sigma confidence. Radius in units of Earth radius, Earth down here, and the mass in units of Earth mass, again, the Earth's down here. There's a bigger range in the mass. The inner planet, the Kepler pipeline initially missed, now dubbed Kepler 36b, has a mass of 4.5 Earth masses and an error bar that's less than 10%. So this, I think, to date, is still the most precisely characterized super-Earth mass planet. If you take the Earth's composition, I think this model is something like 70% rock and 30% iron or so. If you scale that up in mass, it goes right through the posterior distribution, the 1 sigma posterior distribution. And so this is saying that this planet probably has a similar internal composition to Earth. And Leslie Rogers is doing more detailed analysis on this. Others have as well. That larger planet that shows much deeper transits in the river plot is about 8 Earth masses and about 3.7 Earth radii. And so similar in size to Uranus or Neptune, but about half the mass. And just for fun, if this shows the moon over Seattle. If you were to pull Neptune, which is about the size of that outer planet, if you were to pull this close to Earth as these two planets are at their conjunction, then this is what the size of Neptune would appear. And so you'd see really cool conjunctions. Now, one bizarre thing is that these planets are so close, the period ratio is close to 6 to 7, and yet one is very high density, about 8 grams per cc, and the average density of this other one is about that of water. Now, you can take an Earth-like core for this outer planet at 8 Earth masses, and then just pile on a hydrogen-helium envelope, like Uranus or Neptune, and build a mini Neptune, so to speak, model, which is shown by this dashed dot curve. And these were run by Eric Lopez. And this, for 7.5% by mass envelope, is consistent with that outer planet's larger, much larger volume, which gives it the much deeper transits. Lopez and Fortney did some models of atmospheric mass loss and showed that if the two planets started with a almost 60% mass, so both of them much larger in radius, and then lost that envelope with time. This is in log age in gig years. Sorry, this is a gig year. This is a tenth of a gig year. This is 10 gig years. So for the current age of the star, which is about 7 gig years, the outer planet, which is slightly more massive core, 7.4 Earth masses, would have still retained a bit of its envelope for this particular model. And then the inner planet would have lost all of its envelope. Note the 0 point is here, so that explains why, that could explain why the dichotomy between these planets' properties. Okay, so we've wondered, are there additional planets missing in the Kepler data? A former Harvard undergraduate, Ethan Cruzy, who's now a grad student at the University of Washington, has been applying, he's taken over Josh's work and written his own code now, but is applying this to the Kepler data set and has found other planets which are accompanying Kepler objects of interest, the planet candidates. So this shows an example of a KOI found by the Kepler pipeline, which shows significant transit timing variations, again, of order 5 hours. And then he found this new candidate, which shows anti-correlation. Unfortunately, hasn't completed a sinusoid with a similar amplitude. And the periods are close to energy ratio. So they're still working on this. I'm sorry? No, this is just, this structure is not, this is just noise. So this is just from his initial search. Sorry. This is probably noise as well. So these red, this is not a model. This is just his initial transit search algorithm, the quasi-periodic automated transit search algorithm. Returns a list of transit times, and that's what's being plotted here. So they're not to be believed as far as the bumps and wiggles. So we're still working on modeling this. Yeah, thanks. That's a good question. Okay, another missing planet is this one here. You can see I've left a space for it. So these two planets were found around Kepler object of interest 1353. This one has a period of 34 days, and you can see the transits are fairly well detected. Something like of order 40 transits. This is a longer period planet, 125 days, very deep, very high signal-to-noise transits, which is why the blue and green has such good contrast. This one actually displays transit time variations, which you can't see on here. This one, Ethan found with the quasi-periodic algorithm, but he got beat by months by amateurs. So the Planet Hunters website that Deborah Fisher is running, someone spotted this middle planet at something like 66 days. And you can see it has huge transit time variations, which may be why the Kepler pipeline missed it again, much larger than the duration of the transit. You can also, if you look carefully, you can actually see this chopping by eye. It comes and goes, but the red is our best fit model. Joey Schmidt led this paper. He's a grad student at Yale. And we've applied our modeling to it, both numerical and analytical. If you plot the transit timing variations for the outer two planets, as I said, you can see the chopping by eye. Of course, these aren't exactly 2-to-1 commensurability. Otherwise, this phase would hold, but the phase drifts with time, so sometimes it disappears and then comes back. These are our forecasts for the future. The outer giant planet, by the way, this is in minutes, and its huge signal is order hours. This one's in minutes as well, but it only goes up to 20 minutes. So the outer giant planet, which is about a Saturn mass and size, shows amplitude of about 10 minutes. That wasn't visible on the river plot, and it's anti-correlated with the new planet that was found. And so by analyzing the resonant terms, we can get, let's see, we get a constraint that's degenerate between mass and eccentricity. By adding in the chopping of that middle planet, we get a mass constraint on the outer planet. And then by combining the two analytically, we get a constraint on the joint masses. And we find that that middle planet, the new one that was found, is about 5 Earth masses, but very puffy, so it's more like a mini Neptune. And then the outer planet, as I said, is about a Saturn mass. Kat and I also developed a numerical algorithm using symplectic integrator, and that was developed, I guess, 3 summers ago here at CFA during one of my visits. And it's about 20 times faster than doing a boiler store integrator, which is what we were doing before. This is on GitHub if you would be interested in using it. We use a higher order corrector for higher accuracy. One thing that really helped improve the speed was for the Kepler solver, we used previous steps and did a quadratic extrapolation of the eccentric anomaly to the next step, so that in doing the quartic solution to the Kepler's equation, we could converge to machine precision in one step. So that helps speed things up. And then for the transit times, we interpolate between Keplerian drifts from the prior and former and following time steps after a transit has occurred, and then we average between those. And so this speeds up the dynamical analyses. And so if we do a full dynamical analysis with TTV fast, we get this blue posterior, which is in pretty good agreement with the analytic work. So we're confident in these masses as well. Okay, so we're now broadening this, applying it to more planetary systems. And so this shows an incomplete, but it's gradually being filled in, radius mass relation from a recent paper by Jontov Huder et al. The colored points are from our analyses from that particular paper. And what you see here is that there's this boundary between rock and iron, so Earth-like compositions. Kepler 36 is one of these points in here. And there's several other RV points measurements in here too. Transit timing is starting to give other rocky planets. This one has large uncertainties though. And it's finding a lot of planets with gaseous envelopes. So it looks like low mass planets can accrete. I'm not sure what to make of it. There does seem to be a pileup around 4 to 5 Earth masses, and whether that's real or not could be a selection effect, and that these might be harder to detect. And if there's a rising mass function, then that might favor this sort of mass range. So there seems to be a large diversity in the bulk densities of these short period transiting exoplanets, and a lot of that we've learned from transit timing variations. Okay, so let's see. Sorry, I'm going to skip that slide. So to conclude, I think transit timing variations, since Kepler has been launched and since Kepler 9 is the first detection, it's become a thriving subfield of exoplanet research. It is time-consuming, though, to run these models, and we're still plugging our way through individual systems. The TTV fast and other analytic work, I hope, is going to accelerate this. The big surprise is that you can get really low-mass planets that appear to accrete gaseous envelopes, so the so-called mini-Neptunes. Some of them lose those envelopes, though, and so understanding that whole process of evolution of these planet densities is a really interesting theory topic. We're still analyzing the Kepler data, but new data are being gathered with K2. There's a few detections of transit timing variations for transiting exoplanets with K2, despite its shorter duration, 70 some odd days for each field. We're doing ground-based follow-up of Kepler objects of interest that show transit timing variations but didn't necessarily complete a cycle of transit timing variations, and we're trying to get that from the ground for deeper transits. Carolina van Essen is leading KOINet, and one of her collaborators, Sarah, is in the audience. There's also some HST observation follow-up of some Kepler objects of interest, which should be, that's done for atmospheric purposes, but it should be interesting for transit timing as well. And then TESS will be very exciting. It will have an average of 4-week field duration for each field, but at the poles there will be a year-long duration, which should show some TTV systems. Follow-up with JWST would be interesting because of its large aperture, so we could get to higher precision and possibly measure smaller planets and maybe more temperate planets. And so a lot of this work was done in collaboration, and I wanted to acknowledge the Kepler TTV multi-working group, many of whom are in the audience or have been at CFA at some point in time, with whom a lot of this work has been done. So, thank you.
There must be some questions. I'll ask the first one. Okay. Actually, Ramesh has got one there.
So, Eric, you said that when there's only one transiting planet, but there is TTV showing that there is a second planet, but it's kind of tilted.
Doesn't have to be much, but yeah.
Yeah, my question was about the tilt.
Yeah.
So I understand that you don't have enough information to solve for everything, but do you still get any constraint on how much misalignment the two orbits can have?
Yeah, so the question, I don't know if we're recording this, but the question Ramesh asked is how much constraint on inclination do you get from TTVs? And the answer is that it's modest. So it turns out that the TTV signal is fairly insensitive to the mutual inclination. I don't remember the exact numbers, but I think in the KOI 872 system, they constrain the inclination, I want to say of order 10 degrees. It might be a bit larger than that constraint they were able to place. In the case of Kepler 36, we were able to place a constraint on the mutual inclination of less than a few degrees, and that's partly due to the lack of duration variation. So inclination will cause precession, which will then cause the transit chord to vary, which will then cause the duration to vary with time. But we were doing a full flow dynamical model, so that came out of that. So we did get a good constraint in that case. There's another system that I didn't discuss called KOI 142 that shows one very large amplitude transiting planet with the amplitude of a day and many harmonics, and it also shows duration variations. So in that case, I believe they got a very good constraint on the mutual inclination, and I think it was non-zero. I'll have to look back at that. So yeah. In most cases, though, you don't get much inclination.
Can you see three or more, or can you see multiple planets?
Yes. So yes, this has become such a big field. I could just scratch the surface. So let me see if I have that slide. I don't actually have. I didn't show much data. So in this system, the Planet Hunters 3, the inner planet didn't have detectable TTVs, but there are systems with more than 2 planets that show TTVs. One is Kepler 11 by Lecar et al. So this was a slide I had to skip. And Kepler 11 has 6 transiting planets, and there's evidence for TTVs, I think, in either all of them or maybe all but one. And in that case, they're able to derive fairly good constraints on the masses of many of those planets, and some of those points were actually in that mass
you
radius
see all of them
diagram.
in the variation, the time variations? Yeah.
Yeah, so because there's so many planets in that case, it's a little harder to disentangle the signal, so it's only been done numerically, although there are 2 planets that both have large TTV amplitude, and so you can kind of separate them out from the rest of them. And we applied our analytic results to that pair of planets, and we were able to get masses that were consistent with the numerical results. But those are also being perturbed by the other planets, and they are perturbing the other planets. And so you can do a joint fit to the entire system and get the masses of all, at least 5, maybe all 6 planets. There is a 7-planet system that I'm working on, although with my computer crash, it might set me back. And there are several other. There's one, I think, 5-planet system that just got analyzed, and there's several others that are already published.
Impressive, yeah.
Yeah, it's pretty amazing.
Yeah.
Why do you get these near resonances but not actual resonances?
Okay, why do we get near resonances but not actual resonances? I don't have a slide on that, but that's a mystery. So one speculation is that the planets formed further out and migrated in. They didn't necessarily have to form that much further out. You don't need much migration necessarily to cause them to pass maybe into resonance, but then there's some sort of damping that knocks them out of resonance, and that's very poorly understood problem. So but people are actively at work on that. So Konstantin Batigan needs to be here to work on this. The weird thing is that the rate of damping that's been inferred to knock these planets out of resonance but remain near resonance is a very large damping rate. At least that's what the papers say. So stay tuned, though. I know other people are working on this and they have solutions for it. But that's one thought, is that it's migration plus damping, which causes the planets to move out of resonance.
So if you can have an impact on inclination, is it
would you expect every now and then to see a planet just stop transiting?
Oh yes, okay. I wish I could show you a plot that Ethan made of a planet that stops transiting. You see transit, it's fairly long duration, and then gets shorter and shorter and disappears. There's also a paper.
So that should come back, right, at some point?
At some point, yeah, but secular time scale might be, right, pretty long. There's also cases of circumbinary planets. Those can show TTVs as well. And there's, I believe, a case now for a planet that shows transits maybe every other orbit when it happens to be aligned with, slightly inclined, and it has to have the right alignment to cross the star as it crosses the plane of the star, the orbital plane of the two stars. There's also another paper that I think is under review now that's a third planet in a circumbinary planet system that shows transit depths that get slightly deeper. So in the first paper, this is Kepler 47, so the first paper on that, there were one or two blips that kind of look like transits, but they seem, they couldn't be connected to anything else in the light curve. So Jerry Rose called these orphan transits. I think with the second one, they had something like 180-day separation. So I started looking through the light curve, and I found another orphan, another orphan, another orphan. We had a whole orphanage, and it turned out it was the same planet. It's just changing in depth because of, it may not be precession, it could just be near commensurability as well. And the model for that would tell us, but I actually don't remember which it is.
Oh, well, it's related to the other question. With such large deviations, are you too worried these are chaotic systems?
Oh, yes, okay. So that was one thing that Matt pointed out, was that the Kepler 36 system looks similar to Prometheus and Pandora, which is much higher J. And Prometheus and Pandora is chaotic, and so there's a follow-up paper to this system in which Katdek showed that these two planets are chaotic for a large number of the posterior distribution of their properties, with a Lyapunov time that's of order 4,000 to 5,000 days, so extremely short time scale. So potentially bounded chaos. These were integrated for a long period of time and appeared to be stable, but nevertheless showed short Lyapunov time. And Matt can comment on this. Yeah.
That's correct.
Yeah.
It's a very basic question. In general, how well determined are the spectral types and therefore the radii of the central stars in these systems?
Good question. So how well are the spectral types determined? So it depends strongly on which star it is. There's a lot of follow-up that Willie Torres and Dave Latham and many others in this room, probably raise your hand if I'm leaving you out, have been working on following up the host stars of these Kepler planet systems. The best cases, though, are the astroseismic cases. This star is a slightly evolved, the host star of Kepler 36 is something like 1.6 solar radii, so slightly evolved. It's a little bit more massive than the Sun star. And it does show astroseismic variations, and this did have some 1 minute short cadence data, so it was detected. So for this system, one of the reasons the uncertainties are so small is that they take into account the uncertainties on the stellar mass and radius. And if I'm not mistaken, if we can improve the stellar mass and radius a bit more, we actually might decrease those planet mass and radius error bars slightly.
Thanks a lot for a wonderful talk.
Thank you.